Hello, my name is Dontae Milner. I'm from Eastern Illinois University. I had the opportunity to join the NSVP Scholar Associate Program, and I also got paired up to work with Cornell University over the summer. And our project revolved around the cosmic microwave background analysis notebooks and supplements. Below my name are the names of my mentors and the individuals from that I got to work with over the summer. What is a cosmic microwave background and why is it so important? The cosmic microwave background, or the CMB for short, is leftover radiation that was released 380,000 years after the Big Bang, and it is also the strongest evidence proving that the Big Bang happened because every model of the universe needs to explain the cosmic microwave background. Studying the cosmic microwave background helps us to explain the structure of our universe due due to the small temperature fluctuations within the cosmic microwave background itself. Now I am going to talk about the cosmic microwave background notebooks, or the CMB notebooks for short. Jeff McMahon and Renee Hozick from the Simons Observatory at Collaboration and Cornell University had developed these notebooks that will allow students to learn about the cosmic microwave background in a different way. These notebooks were made by using Jupyter, which is an open source coding program that allows for interactive coding exercises from which students can learn from. But, however, due to COVID, this program had to become remote. This slide is an example of what the notebooks look like, and in the top right corner is a picture of the students that were in the summer school program. Now, I am going to talk about the cosmic macro background notebook supplements, or the CMB supplements for short. Two undergrad students from Cornell University, Kushama and Pedro, created a companion guide to go along with the GitHub Jupyter notebooks written by Jeff McMahon and Renee Hozick. This slide is an example of what the CMB supplements look like, and from the supplements, it does talk about discrete Fourier transformations. As I said, with the supplements being a companion guide for the notebooks, it provides background knowledge and sometimes dives deeper into certain topics that were not covered in the notebook. These supplements also offer hints to help students try to complete the notebook exercises. Now I am going to talk about my involvement that I had with the Cosmic Micro background notebooks and supplements. Mm, my involvement with the project included giving feedback on the notebooks and the supplements. From the perspective of someone who was not an expert on this subject, the subject, of course, being the cosmic microwave background. This feedback including just things such as asking questions, looking for extra resources that can be used, and also giving suggestions. This was important because it allowed for edits to be made that will help students who are learning from these notebooks who are relying on the supplements. One major suggestion I made was to add line numbers in earlier chapters of the supplements so that it'll be easier for those to follow along who are using the notebooks with the supplements. Now I am going to talk about what I learned from the cosmic microwave background notebooks and supplements. I am I am also going to take you through through the different CMB maps and also what they do, and at the end show you a completed CMB map. This slide, this first map we have a temperature and a entropy map, or a flat sky approximation map. In order to generate this map, first we generate a 2D power spectrum by 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 revolving the power spectrum around the axis in polar coordinates. Then we generate a Gaussian random map with the unit variance as our random realization. Then we multiply that maps from 1 to 2, and by using Fourier transformation, we get this map in real space. We provide a function to do this and a function to plot this and other maps with a uniform color scale. We will use this map to create our full CMB map later, and this map will serve as the foundation for creating other maps. Now on this slide, I am going to talk about the Sayanov-Dolce map or the Sayanov-Dolce effect from galaxy clusters. The Sayanov-Dolce effect happens when high-density charged particles, such as the ones that can be detected at galaxy clusters, transfer some of their energy into the cosmic microwave background photons, causing them to scatter. We create a Sayanov-Dolce map to try to track these large clusters that will cause the CMB photons to scatter. To do this, we treat each cluster as having a brightness beta profile in which each cluster will have a identical angular size. We draw the distribution of central temperatures from the external distribution to simplify the code and to reduce the dependence on the external libraries. And from you see this is the SZ map that we get. This slide, I am going to talk about noise filtering, such as white noise, atmospheric noise, and peak noise. As I said, there are three different kinds of noise to deal with, and that being atmospheric noise, white noise, and peak noise. White noise is a random signal having equal intensity at different frequencies. Pink noise, or 1 over F noise, resembles white noise but instead falls within a frequency, and atmospheric noise is is radio noise is radio noise, produced by natural processes in the atmosphere. Ground-based cosmic microwave background instruments suffers from these types of noise and interference. And in order to generate this map, we can simulate these types of noise interference into Fourier space, which in map form looks similar to the flat sky approximation map that we first made. And by combining all of these maps into one we get our completed CMB map. So as you can see, we see the temperature differences, that being our temperature and astrography map. We see the lines within the map itself, that being our noise filtering map, and these little tiny dots that we can see that is from those are our galaxy clusters that are being detected from our Sayanov-Dolce map. I just want to thank you for coming with me through this presentation. I also wanted to give thanks to NSBP, especially Casey Wagner, the Simons Observatory, and Cornell University for this opportunity. Once again, my name is Dontae Milner from Eastern Illinois University. Thank you for watching.